Continuing with our video and spectroscopy, I have this spectrum here, and we want to find out what's the structural formula. Well, again, I have at around 7 parts per million, I have this huge peak here integrated into 4 hydrogens. Now remember we said that anything around 7, usually think of it as an aromatic ring. So I'm going to draw my aromatic ring. Right, and this has 4 hydrogens, which means that this has to be di substituted, right? Because remember there's 6 hydrogens on an aromatic ring, so this has to be di substituted, right? So we already took care of 6 hydrogens. The molecular formula is just C10H14, so we took care of 6 carbons. Now I see that I have a hydrogen here. I see that I have a CH3 here, right? That splits to 1, right? It splits to 1. So maybe I have a methyl group here, right? And see how that makes sense. I have a methyl group here with 3 CH3s. Well, not 3 CH3, but 3 hydrogens, which are the CH3s, and they have 0 neighbors. So 0 plus 1 is 1, and that gives me a singlet, which is exactly what we see here. So that takes care of that part. So therefore, I can't do anything else on this side of the molecule. So therefore, I have to go to this side of the carbon chain, right? So I have 6 hydrogens that's both split in split in twice. That gives me a doublet, right? Gives me a doublet. So the those 6 hydrogens split twice, which means that it gives me a doublet, right? So maybe I should draw a carbon, a carbon there, right? And I have 1 hydrogen that's split in multiple times. So if I have 1 hydrogen, therefore this has to be a methyl group, and this has to be a methyl group. I have this 1 hydrogen here. Look how many neighbors it has. It has these methyl protons and these methyl protons. Well, this whole multiplet here is the result of these protons all around here. So therefore, this has to be the molecular formula. And look how it makes sense. We have this 1 hydrogen here that's split in multiple times. And then we have the 6 hydrogens here. And they both only have 1 neighbor. They both only have 1 neighbor, which is why we're seeing a doublet there, right? With them integrating that 6 hydrogens. So the molecular formula for this spectrum will be this. Now guys, this is just a shorthand way of drawing an aromatic ring, so don't be freaked out. Usually in organic chemistry too, you guys will see more of that as you'll be dealing with a lot of reactions with the aromatic ring. And kind of look how this makes sense. If you remember IR spectroscopy, this is actually at around 300 centimeters inverse, with a huge peak like this. This usually represents an aromatic functional group. So that's just another way of telling that our stuff is actually right. Right. And to be honest with you, we could actually calculate the degrees of unsaturation of this molecule and see if it makes sense to, right? Remember, we said that the molecular formula is C10H14. So therefore, the degrees of unsaturation is C10. 2 times 10 is 20, plus 2 is H22. Well, H22. Well, 22 minus 14 is what? 10, 8. 22 minus 14 is 8. And we're going to divide that by 2, and we have 4 degrees of unsaturation. Well, remember, a ring count as 1 degrees of unsaturation. These double bond, that's 2, 3, 4, which is exactly what we see in our molecule. So that's another way of telling that you're actually correct.